Then we have Rolle's theorem, or sometimes it's referred to as Rolle's theorem. Whichever you prefer, it doesn't really make a difference. Now, the Rolle's theorem is really just a special case of the mean value theorem. So you still need to have a closed interval, still needs to be continuous, and still needs to be differential. The extra thing here with Rolle's theorem is that the two endpoints, when you plug them in, have to be equal. They have to be at the same height. Well, if they're at the same height, that means our slope is 0. Now, the mean value theorem says your derivative has to be equal to your slope. Well, Rolle's theorem still says the same thing. Your derivative has to be equal to your slope, but the slope between the two endpoints, since they're at the same height, is 0. So we just say our derivative has to be 0. Now, in this case, we could apply Rolle's theorem. We could not here because it's got a cusp here, so it's not differentiable there. So here we go. Can we use Rolle's theorem here? Well, first of all, we got to figure out where we're equal to 0. So we figure it out. Plug in 0 here. Solve it. Oh, we could pull out that common factor. We have two things multiplied together. Set the first one equal to 0. Square both sides to get x by itself. Set the second one equal to 0. Solve it for x. These are our two endpoints. So the question is it differential between 0 and 1? Is it continuous between 0 and 1? And when we plug in 0 and when we plug in 1, do we get the same height? Those are the things you got to ask yourself before you can apply Rolle's theorem. Well, when you look at your graph, oh, yep, I can draw it all between 0 and 1. Oh, my derivative would exist. I have no vertical asymptotes. I have no cusps, anything like that. So it's differentiable. It's continuous. And hey, when I plug in 0, I get a height of 0. When I plug in 1, I get a height of 0. So when I plug in these two values, I get the same y value. So my derivative has to be equal to my slope of 0. Well, I can go ahead and do my derivative here. Put the exponent in front, decrease it by 1. Put the exponent in front, decrease it by 1. Pull out my common factor. Woo! There we go! So now all I have to do is take my derivative, set it equal to 0. And you might be wondering, oh, what happened to that over 2 and the square root of x that would be on the bottom? Well, the only way a derivative is ever going to be equal to 0, the only way a function's ever equal to 0 is when the top of a fraction is 0. So I didn't have to be concerned about this part here that would be down in the bottom. So I finished solving this for 0. And I get x to be 1/3. Now, is 1/3 between my two numbers of 0 and 1? Oh, by George, it is. So my answer is 1/3. So if I'm at 1/3 on my function, x being 1/3, I need to have the same slope here as I did going between these two here. I need to have a slope of 0. Well, that's the case. Now, if you would have ended up having multiple answers here, and the answer that you would be looking for would have to be between the two endpoints you had of 0 and 1. Oh, mean value theorem and Rolle's theorem can help catch speeders on tollways. So take a little bit and read through this.